Large-scale AI for a better tomorrow. Hello, everyone. Welcome to the 7th Samsung AI Forum 2023. My name is Kyung Kim. It is indeed my great joy and privilege to stand before you as an MC in this meaningful event. Let me greet you. Thank you very much for joining us. Today, Samsung Advanced Institute of Technology has invited world-renowned scholars and experts in the field of AI and CE to share the latest AI research trends and explore innovation direction. We hope that the forum will accelerate the expansion of the global AI and CE research ecosystem. Also, we'll hold the award ceremony of the Samsung AI researcher to recognize outstanding researchers in the field of AI and the Samsung AI C Challenge competition. In addition, the forum will include a poster presentation of excellent papers and networking program for researchers to promote and enhance the research ecosystem in the field of AI and CE. I hope you enjoy every program that we have prepared for you today. Then now, let's start the forum with an opening speech by Kyung, President and CEO of Samsung Electronics. President and CEO Kyung was not able to attend today in person due to unavoidable circumstances. So let's meet him through a video and take a look.
Greetings and welcome from all corners of the globe. Samsung AI Forum has long served as a meeting ground for the brightest minds in the field of artificial intelligence, providing a platform to discuss both the present and future of AI. I'm deeply honored to kick off the 7th edition of the Samsung AI Forum, and I would like to extend a heartfelt thank you to all who have made the time to be part of this forum. I know you are busy. I'd especially like to thank our esteemed speakers who join us today from all over the world. While the world has indeed made strides in overcoming the pandemic, we are not out of the woods yet. There are still environmental, political, and economic challenges we must overcome, and we will together. Recently, the spotlight has shifted toward generative AI. Already, technologies such as large language models and image generation models have captivated billions and reshaped the world. Large language models operate by acquiring facts and knowledge from trillions of pieces of human-generated text. We can use these tools to leverage the vast pool of human wisdom. They provide us with the potential to unlock new solutions and address long-standing challenges, and there are possibilities we are not even yet aware of. However, large language models and generative AI come with their own unique set of challenges, namely safety, trustworthiness, and sustainability. Safety concerns range from privacy infringement to existential threat to humanity, as raised by renowned scholars like Dr. Yoshua Bengio. Ensuring the trustworthiness of these models demands tackling the hallucination problem. Finally, the sustainable growth of generative AI requires achieving significantly more energy-efficient computation for training and inference. Samsung seeks to engage in discussions and collaborative efforts aimed at solving these issues while working together to co-create a brighter future one driven by AI and powered by semiconductors. We envision Samsung AI Forum as a catalyst in realizing this goal. Innovation across algorithms, data, and computation is necessary for large-scale AI systems. Samsung will continue to play a pivotal role in bolstering the AI ecosystem with critical components for AI computing systems, including high-bandwidth memory chips. We have been dedicated to harnessing AI to optimize semiconductor development and manufacturing processes. Samsung also firmly believes that generative AI, such as large language models, may solve the industry's most daunting challenges. Samsung is thrilled to bring together the foremost experts and researchers from both academia and industry. I have no doubt that our distinguished speakers will inform and inspire us here today. And I cannot wait to discover how AI can help shape a better tomorrow.
Then now we are honored to invite Professor Yoshua Bengio of the University of Montreal for a keynote speech. Professor Bengio's presentation today is titled on Towards a Safe AI Scientist System. As Professor Bengio is abroad, we'll meet him via a video call. So ladies and gentlemen, please welcome him with a big round of applause.
Hello. Thanks for the introduction. Do you hear me well?
Yeah, we can hear you well. Thank you very much, Bengio. Professor, please start your lecture. Yes.
So I'm going to tell you about some of the issues with current LLMs and generative AI from a point of view of safety and reliability. And I'm going to talk about an approach that follows on a lot of the work that I've discussed at the AI Forum in the last few years for neural networks that model the world just like scientists do. That's something I call the AI scientist. Right. Indeed, the problem of hallucination is a very big issue, both because of practical applications when we deploy these generative AI systems. We don't want them to make confidently wrong statements that could be both bad for the user, but also introduce some safety issues. And I'll explain, why. But maybe a few clues as to why the current AI systems are missing something. This is something I've been studying for many years now. The current neural nets, they perform similarly to human intuition, also known as System 1. In other words, there is no filter for what is generated. There's no reasoning, which is more System 2. And they don't really have a notion of what is true. Instead, they're just imitating how humans have produced text in their training data. So this is a problem because we'd like to use natural language to instruct them to behave in particular ways. And right now, there are two methods that we use in LLMs to specify what we want. One of them is training them with human feedback and training a reward function from actual feedback from humans and fine-tuning with a reinforcement learning objective. And the other way is at runtime, we use prompts and pre-prompts, which are natural language instructions. But actually, there is no guarantee that the AI system will follow our instructions. Worse than that, we see that very often it doesn't, or that it can be hacked by changing the prompt or fine-tuning so that it would behave contrary to the instructions that were given. And that's an issue because these systems could be misused. We call this mismatch between the behavior of the AI and human intentions misalignment. We'd like instead to be able to train AI systems that are aligned. Part of the problem is this reward function that we train is not really what we want. It's a very poor approximation. And unfortunately, there is no formal description of our intention. We can say it in words, but it's not very clear to the machine what we actually mean. And this mismatch can actually be dangerous as well. As we build computers that are gradually more and more powerful, they could be both more useful, more beneficial, and also more dangerous if they're used in malicious ways. And this is something very concerning as we move towards potentially human-level AI systems, also known as artificial general intelligence or AGI. It's not clear that our current social structure is ready for this. Are we wise enough, individually or collectively? I'm not sure. The other problem is that as we make those systems more powerful, if somebody can give them new goals, they can use the abilities of the system, the ability to solve problems and to answer questions for purposes that were not intended or maybe are even illegal. So there are a lot of concern that especially the open source AI systems could be used for fraud, could be used by bad actors, terrorists, and some states that may want to use this militarily or to destabilize democracy, to create bioweapons, chemical weapons. There are a lot of concerns that these systems, at least maybe not the ones that currently exist, but as we see the trend, the systems we might have next year or in 2 years or 3 years, as we move forward, they become more capable, they know more things, and we need to find ways to control them so that they are better aligned to our norms, our laws, and the intentions of the engineers who designed them. So this question of alignment is really central. Unfortunately, right now, the science of AI doesn't know the answer to the question, how do we design an AI system that behaves according to our intentions? And this is crucial because we would like these AI systems to behave morally, as I said. Now, as these systems become more powerful, the misbehavior could be more dangerous. And the worst case scenario is that they become so good in some aspects of their knowledge that they could surpass us. For example, in cybersecurity or in being able to influence people. And there is a lot of literature about how even unintentionally we could end up with AI systems that we lose control of, that behave as if they had their own self-preservation objective. For example, with what is called reward hacking. And this would be like creating a new type of entity that has its own survival as an objective. There are also human beings who unfortunately want to build AI systems that have their own self-interests. just like us, like every living thing has a self-preservation goal. In either case, this might create a kind of new, potentially dangerous species that could dominate us if it's stronger than us in a few crucial areas. So, why would we eventually get AI systems that are more powerful than us? Well, our brains are machines. They're biological machines. And in addition, AI systems are built on digital computers. Now, digital computers have both advantages and disadvantages over brains. The disadvantage is that digital hardware requires a lot more energy, power, energy consumption compared to analog. But we have a lot of electricity nowadays. But the advantage for digital computers is that they have huge communication bandwidth, and they have access to much more precise memory. In fact, they can learn faster because we can parallelize training much more easily than between humans. So there's a lot of uncertainty about when these superhuman abilities will emerge, but it could be a few years or decades. It's hard to say. In any case, it would be good to solve this problem to make sure that the AI systems are aligned to do what we want before we get there. So let's try to consider a little bit more technically now what it is that can make an AI system not safe or dangerous if it's in the wrong hands or if we lose control of it. There are three aspects. One is its capabilities. So its problem-solving abilities, its knowledge. The second is agency, meaning what can it do? Does it have access to the internet? What sorts of is it enclosed in a kind of constrained environment where it cannot directly access the real world? So this is what its action power is. Does it have access to a bank account? That's bad. And then the third aspect is alignment that I've been talking about. And how misaligned is it? Maybe you can't have perfect alignment, but how close can we get to human type of alignment? We are aligned with each other to some extent, but not perfectly either. Okay. So let's see one scenario which has been worrisome for many researchers. When we build different AI systems and we consider the danger of loss of control, it turns out that different types of AI systems are not all as dangerous. So maybe the worst scenario, as I'll try to explain, is model-free reinforcement learning, where you're looking at long-term rewards. In other words, the AI systems can strategize. Fundamentally, the reason for this is that when we do reinforcement learning, we can be amplifying the misalignment. And I'm going to try to explain that. As I said, when we train with reinforcement learning with human feedback, this is the way we currently train large language models for chatbots, for example, we don't know what the reward function should be. So we use a proxy for the reward function. By the way, this is also something we use in many other applications, like in scientific discovery. So we use data, like human feedback, in order to train a reward function. And of course, that reward function is not the true reward function. It's not what we want. It's an approximation of what we want. But then we optimize this approximate reward function, and it may find solutions that may be too good to be true. So when we maximize this incorrect thing, we may end up discovering, falsely good solutions. And we may amplify the misalignment. I think I have a slide which illustrates this. Yeah. So if you have two functions, like the green one maybe is the true reward, and the red one is the whichever is the estimated one. Now, if we make a random sample, it may look in most places like they're pretty close to each other. But when you optimize the red one, let's say, you're going to find some places where it's really high. And in general, this is going to be too good to be true. And so when that happens, the system behaves in a way that's unrelated to whether it's good or bad for us. By the way, this is important in the problem of misuse. We'd like to build LLMs that cannot be easily misused by bad actors, by criminals. And we need to make sure that the reward it gets for behaving well corresponds to what we actually want. This is connected to the problem of what's called reward hacking, where an AI that's sufficiently powerful in its ability to maximize the reward actually ends up finding a really weird behavior in which it takes over its own provision of reward. It produces, for example, it can hack the computer that is supposed to record your feedback, and now it gives itself positive feedback, and then it doesn't really care about what we really want. It provides itself the rewards, and we lost control of it. Okay, so now let's start talking a little bit about solutions. One interesting piece of information is that if instead of maximizing the reward, which is normally what we do in reinforcement learning, we use something like maximum entropy reinforcement learning, which approximately is going to sample proportionate to the reward, which is also what we do with generative flow network, something I've been talking about here in previous years. You change the task that the learner is trying to solve, and you get something that is not trying to maximize reward, but it's trying to behave in a more random way, more stochastic way, so that it prefers to behave in ways that have a high reward, but sometimes, it also chooses something that's slightly less good. And it turns out that this makes these systems much more robust to the mismatch between the true reward function and the reward function it's given. This is connected to another important concept when we're thinking about how to make AI systems more reliable and more faithful, and avoid confidently wrong answers. And it's the idea of being Bayesian. So to understand this, you have to know that when you consider any data set, usually there could be multiple models or multiple interpretations or multiple theories that are compatible with that data or that experience. The way we usually train machine learning with maximum likelihood or model free reinforcement learning is going to choose one of these interpretations, one of these theories. And it might be a good theory or it might be a wrong one. In fact, the majority are going to be wrong. And that's why those systems can be confidently wrong. If you pick the wrong theory, it might be certain that it has the right answer, but actually because it's the wrong theory, you're going to have a wrong answer. So what can you do? Well, if you take into consideration that there are multiple theories and you don't know which one is correct, then you can make a more correct probabilistic calculation, which is called the Bayesian averaging. which tells you not only what the consensus answer is, but also how much uncertainty there is, because different theories that are compatible with the data produce different answers. And in particular, in order to make sure AI systems are going to be consistent with what humans want, which is something that we cannot perfectly provide to the computer, only give it some clues like feedback, human feedback in LLMs. It's important that the AI system remain probabilistic about our intentions. It doesn't really know what we want, and so it needs to keep a kind of Bayesian model that captures that uncertainty, that it's got only like finite amount of information about what we really want. And so if it keeps that uncertainty explicitly in its calculations, we can avoid a lot of the problems I've been talking about. And when it's not sure what action to take, or if it considers an action that, like an answer to a question, that may be harmful according to one of the theories that fits the data, then it would be better if the AI system just reject the action, doesn't do anything. And it's fine because there's a special action, which is no answer, which corresponds to saying, well, we're going to let the humans behave and choose what to do. So when it's not sure if its action could be harmful, it should not be acting and let the human do what they have to do. All right, so that's very important, the uncertainty, what's called epistemic uncertainty aspect. Now, when we consider how to make the system better know, if some action or some answer could be harmful, the only reasonable way that it could do this if it had a good model of how the world works. In order to figure out that the potential answer could be, for example, misused or could eventually harm somebody, it needs to be able to reason over an understanding of how the world works. So this is really a kind of world model that the system needs to build. And this is also a subject I've been working on quite a bit in the last few years. How do we train neural nets so that they could learn a distribution over a world model? So a world model is like a theory for how the world works. And there are some advantages to learning a world model, which is different from the way we currently train neural nets. The way we currently train neural nets is we directly train them to produce answers given questions. And this might be inefficient from a statistical perspective, because the alternative is to separately learn a world model and how to answer questions given that world model. And the advantage here would be you need less data, because usually to describe how the world works, for example, think about physics, you need less bits of information than in order to answer questions, which is called inference. In fact, one reason I think why this model-based approach in reinforcement learning has not picked up in the last few years is because people have been trying to do model-based reinforcement learning using maximum likelihood models instead of Bayesian models. And the problem with that is what I was talking about before. If the maximum likelihood model is wrong in just a few places, and it's confidently wrong, then when we train the policy of the AI, like how it answers questions, it may zoom in on these places where it thinks it discovers something really good, something that's really worth a lot of reward. And usually, again, that's going to be too good to be true. So it discovers like fantasy treasures, which corresponds to hallucinations. So to do the model-based approach, which is going to be more efficient from a statistical perspective, so it should generalize better, we also need to be Bayesian, especially in the context where we're doing reinforcement learning, because otherwise the reinforcement learning is going to do this optimization I've been talking about, which is going to find those places where it thinks the reward is really large. And in fact, it will be, unrelated to reality, and it starts saying or doing really bad things. To understand why being Bayesian is safer, let's consider a very simple scenario. Imagine you have an agent. It is in front of two doors. There's a left door and the right door. And based on the data that it has seen, there are two theories that are compatible with the data, but it doesn't know which one is correct. If it was doing maximum likelihood, it would pick one of the theories kind of randomly. Any one would fit the data, and so one of them will be chosen. But if it's Bayesian, it's going to consider all theories together. So let's see what the theories could be to illustrate what can go wrong. Let's say that the first theory says that behind the left door, there's a mortal danger, something not safe, something really, you die. And then behind the right door, you get some cake, something good. The second theory says behind the left door, you get some cake. Behind the right door, nothing good, nothing bad. Okay. So again, if you're doing maximum likelihood, you have 50% chance of picking the wrong theory. Let's say that the right theory is the first one, and you pick the second one. So now you're going to go left because you think there's some cake, but then you die. So 50% of the chances of dying. If you're Bayesian, well, you know that the two theories are compatible with the data, but you don't know which one is correct. And of course, you don't want to die, so you're going to take the right door, because on the right door, either you get some cake or you get nothing. That's much better than the left door, where you get some cake or you die. So you see why being Bayesian is the safe thing to do when there are some dangerous potential actions. Okay, so why is it that not everyone is already doing Bayesian calculations? Well, we don't know how to do it right. The exact Bayesian calculations are computationally intractable. There exists some Bayesian modeling, but they make very strong assumptions that are typically not correct. And so they end up with parametric modeling that doesn't work as well as neural nets that are like non-parametric, that allow any kind of answer, more or less. But something has changed in the last few years, which is we can use neural nets to estimate Bayesian posteriors. We can train neural nets to approximate these conditional probabilities. And generative flow networks, which I've talked about, is one of these methods. So before I go on with generative flow networks, so GFlow nets, let me tell you what is the problem we're trying to solve with a Bayesian machine learning system that would be safer. We decompose the problem in two parts. One part is building a kind of understanding machine. So it's an AI system that, like, think of a neural net, like an LLM, that produces theories like how the world works or some aspect of the world. And we can call these theories data. And we also train a second neural net, which is like current LLMs. So you give it a question, it produces an answer. Now, we can use the data to train the first LLM, and then we can use the first LLM to train the second LLM. What's interesting is the first LLM, which is just trying to understand how the world works, is not acting in the world. It's just trying to make sense of the world. It's really like an oracle. And we could use it to help scientists discover interesting things. There's a wrong belief in the AI community that we necessarily have to build AI systems that have agency, that act in the world, because we act in the world. But actually, there's a lot of things that AI systems could do to help us to come up with better explanations or understanding or answers to questions without having to ever act in the world. And that would be a lot safer when we build AI systems that are more powerful. Also, if we were able to train such an AI scientist that is able to answer questions but doesn't act in the world, we could use it to check the safety of another AI system which could act in the world, for example, in a dialogue system. So the idea is very simple, and you could have many variations on that theme. The idea is that this AI scientist, which is this Bayesian posterior thing, can answer questions like, what is the harm that may come if the agent performs a particular action in a given state? So in the case of a dialogue system, the action is an answer, and the state is the context and the query. And we can use the AI scientist now to estimate probabilities for harm in this context. And if the probability for harm is above a threshold, then we might just reject the action and decide not to produce it. So that's the idea to make safe AI systems. Now, there's a really nice property of this kind of approach. I only have a conjecture, and I would like to prove it more formally. But what the conjecture says is that if we build these kind of Bayesian model-based approach to predict harm or human intentions, the alignment with human intentions, the conjecture is that the more we train the neural net that we use for the model and for the answering, the safer the system. And the reason is very simple, is that we can prove that the neural net objective, like in a GFlow-net, for example, has a property that as we get the training objective to 0, as we minimize the training objective, we converge to the correct Bayesian posterior, which isn't trying to deceive anyone. It's just trying to be as truthful, including about its own uncertainty, as possible. So this is something very appealing. This idea of using neural nets to approximate inference is something that's already being used, for example, in research, in material discovery, in drug discovery, in scientific research. And being able to estimate the correct conditional probabilities for answering all kinds of questions would be extremely useful from the point of view of building safe and reliable AI systems. So what is important here is that we use the neural nets to do what is called amortized inference, which means that we train it to approximate the correct probabilities with an objective that has the property that the better we train the neural net, the bigger the neural net, the closer it gets to the absolute correct answer. Now, the absolute correct answer may be something intractable, but that's what we usually do with neural nets. We train them with an objective. It's trying to solve a problem that is intractable, but the bigger the neural net, the more we train it, the better it gets at approximating and minimizing the objective. And that's the beauty of neural nets. So, to summarize, we have, I think, some good reasons to hope that the alignment problem could be solved. And to see how we can get there, first of all, start with a remark that if we knew the correct reward function, or like we knew a program that says whether an action by an AI is good, is safe, is beneficial, then the problem would be solved. We would just apply that function each time we do an action to make sure we only do safe things. Well, obviously, we don't have that function. But imagine we had a model of a wise and virtuous human being that could not be tempered by an AI because it's not a real thing. It's a model that's sitting in the mind of the AI. If we knew that model, it would be pretty much as good as if we had the right thing. But of course, we don't know what a wise and virtuous human judgment would be. However, we can make a probabilistic model of that, a Bayesian posterior over all the possible such models. And the difference with the true model is that it would tell us when it's not sure what the virtuous human would say. Okay, so that Bayesian posterior is something that's less informative because it has uncertainty about what the answer should be. But when it doesn't know, at least it does something safe. Now, we're not even able to do that because that's intractable. But in principle, with infinite compute, we could do that. That's where amortized inference comes in, which is now going to approximate that Bayesian posterior. And we know that as we increase accuracy of that neural net, its training objective, we approach that Bayesian posterior. So that's it. Thank you for your attention, and please take the time to think about the complicated questions I've been discussing, and I'm happy to answer questions.
Thank you very much, Professor Yoshua, for your insights, sharing your insight with us. As promised earlier, we would like to open the floor to our audience for a brief Q&A session. So if you have a question, please raise your hand and we'll deliver the microphone to you. First come, first served. Please raise your hand. Any question from the floor? 네, Q&A 시간으로 넘어가겠습니다. 저희가 동시 통역 서비스를 제공하고 있기 때문에 편하신 언어로 말씀해 주시면 네, 통역 수신기가 작동을 잘 하고 있습니다. 편한 언어로 질문을 해주시면 되겠습니다. 바로 앞에 분 계속 손을 들어주시겠습니까? 네.
Thank you for the inspiring talk, Yoshua. I hope you're doing well.
Yes, thank you.
And also, it's great to hear talk about hope from you. And it's exciting, and I'm sure I need a lot of time to consume your talk and understand it fully. But I have just a simple question. You talked about separating the world model from agency. And agency is still AI model itself, isn't it?
Well, we have applications where we need agency. If you do a dialogue, of course, it's interacting with some real person, so it's an agent. There are also applications of AI where you don't need agency. So again, think about in drug discovery or material discovery. If you train a just supervised learning system that tries to predict the property of a material, there is no agency, right? But what I've talked about is when you separate the ability to understand the world, to answer questions like an oracle, from the agent part, you can get systems that would be more efficient statistically, but also safer, because we could use the oracle, if it's Bayesian, so it knows about its own uncertainty, in order to be more conservative when it takes a decision.
Thank you very much for the great question and answer. Any other question from the floor? Please raise your hand. Yes, over there, please.
Thank you for the talk. And I want to ask about the prior distribution. So in order to move towards the Bayesian approach, we have to design a useful prior. But when I read some ML papers and AI papers, the prior distribution usually used as just a unique Gaussians or something kind of a regularization proposed. they only use for. So I think the AI researchers have to start to study about which kind of prior distribution will be useful to reduce some kind of hallucinations or something. So do you think there some kind of movements will be like that to study the
Right. So I didn't have a lot of time to explain the technical details of my research. But the kind of so first of all, in standard machine learning, like deep learning, we already use priors. The architecture of the neural net is a prior. The fact that we initialize in a particular way is a prior. The fact that we use stochastic gradient descent is kind of inducing some sort of implicit prior. So we always use prior, even if we're not Bayesian, right? The other thing is, for the particular kind of world model I'm talking about, the thing that we want the neural net to be having a prior over is a theory of how the world works, or at least some aspect of the world. And that theory itself is not necessarily a neural net. It might be more like a piece of text, and or like a set of formula, if you want, or a program. Thinking about it as a program is the better way. And in the space of objects like programs, there's a very natural prior that's been studied by mathematicians for many decades. It's like the Kolmogorov prior. So it's just 2 to the minus length of the program. It's, if you want, like, just the log of prior is the number of bits of information, and that's it. It's Occam's razor. Occam's razor is saying simple solutions are more probable than more complicated solutions, where complicated just means how many bits of information you need to specify this. This is the best prior, if we can use it.
Thank you very much, Professor. Well, because we're a little behind the schedule, I'm afraid that would be the last question from the floor. So please raise your hands. That will be the last one.
Thank you very much for your wonderful speech. I come from Korea Consumer Agency. My agency work for consumer protection and consumer safety. OECD is working for monitoring for AI incidents. So the program's name is OECD AI Incidents Monitors, which is exactly the monitoring the AI incidents all around the world. For example, like self-driving AI cars occurring, the traffic accidents, so that the people are hurt, people are dying and hurting, something like that. So OECD is making effort to protect the consumers from AI itself. So this is my question as a scientist who is making effort to promote the safer use of AI. Do you have any good advice for regulators who also want to protect consumers and all people who use AI?
Yes, thanks for the great question. So last week I was in the United Kingdom for the UK AI Safety Summit. There were a lot of countries, and South Korea, Republic of Korea, has accepted to host next meeting of the AI Safety Summit. So there were a lot of discussions about regulation and safety. And my recommendation that I've discussed there is that it should be the responsibility of companies or organizations that are building and deploying AI systems to demonstrate that their system will be safe before it is deployed. So this is like you're guilty unless proven innocent, rather than the current approach, which is you're innocent until proven guilty by the government. So the government is trying to find some tests to show that your AI system is going to be dangerous. So I think we should reverse the burden of the proof. Also, because currently the expertise for understanding the safety of AI is mostly in companies. Governments should, develop the right expertise and hire the people, but it's going to take some time. So I think it makes a lot more sense that, like in drug discovery, for example, the pharmaceutical companies have to prepare a kind of report, a scientific evidence to convince the government and the regulator, neutral academics, that their science is sound, that their drug is safe. And we should do the same thing for AI.
Thank you very much, Professor Yoshua. This is the end of the Q&A session. Thank you once again. 여러분 큰 박수 부탁드리겠습니다. Yes, that was truly enlightening conversations with Mr. Professor. Thank you very much for your active participation as well. So now we are going to announce the winners of the 2023 Samsung AI Researcher Award. And there will be the winners' acceptance speeches as well. And first, I would like to invite Kyung, Corporate President of Samsung Advanced Institute of Technology, as he will help with the proceedings. So, Corporate President, please come up to the stage. 네, 시상을 위해서 진교영 사장님을 먼저 무대 위로 모시도록 하겠습니다. So now we're going to announce the winners of the 2023 Samsung AI Researcher Award. First, we have Jason Lee of the Princeton University. Congratulations. Please come up to the stage. 네, 여러분 박수로 축하해 주십시오. And also we have Xiang Ren from the University of Southern California. Congratulations. Also, please come up to the stage. And we have Emma Pearson of the Cornell University. Please look at the screen. And also we have Virginia Smith of the Carnegie Mellon University. Congratulations. And Connor Gray from the Massachusetts Institute of Technology. And they are not able to attend due to unavoidable circumstances. So we'll meet them online. 네, 오늘 세 분의 수상자는 자리 함께 해주지 못하셔서요. 영상을 통해서 지금 함께하고 계십니다. 여러분, 큰 박수로 축하해 주십시오. Please wave your hands. Congratulations. Thank you very much. And now we have all the awardees on stage. We're going to continue the award ceremony. So first, we're going to present the award to Jason Lee at Princeton University. 네, 사장님께서 이제 시상에 수고를 해주시겠습니다. 먼저 Jason Lee at Princeton University. Congratulations. 여러분 다시 한번 축하의 박수를 부탁드리겠습니다. 네, congratulations, Xiang Len from the University of Southern California. 자, 이제 트로피와 상장을 받으셨고요. 세 분 함께 기념사진 촬영을 진행하도록 하겠습니다. Congratulations once again. We're going to have a commemorative photo together. Thank you very much. So, yes, we're count to three. Let's say AI all together with big smile. 3, 2, 1, AI. Put a big smile. 네, 이렇게 사진 촬영 마무리를 하도록 하겠습니다. So this is the end of a group photo session. And now we will be delivering the acceptance speeches from the awardees. Jason Lee, please stand by. Thank you once again, Corporate President, for your hard work.
Hi, everyone. Thank you for having me here today. I work on the theoretical foundations of deep learning. So I think all of us know that deep learning has really changed the world since its successes in 2012. And especially prominent today is the success of large language models in natural language processing. Deep learning started with speech recognition in 2011. And then also, of course, computer vision was completely revolutionized around 2012. So it's very clear deep learning works in practice. I think the empirical evidence for this is overwhelming. And all of us are here today because deep learning has made AI a possibility. So of course, here's even more successes, all from the past 10 years. Computer vision, language, like I said, reinforcement learning in playing games, starting with Atari, single-agent reinforcement learning, then multi-agent, two-player zero-sum games such as Go, multi-agent games, StarCraft, Dota, AlphaFold, and in AI for Science. And for the past 10 years, people have predicted that AI will change the entire world. And then Andrew said AI is the new electricity. OK, and this is completely driven by an empirical paradigm of a data set and then compute, and then lots and lots of hyperparameter tuning, typically our graduate students and now in the industry. And this leads to better and better error rates. At least this was the paradigm in computer vision. And every year you see the ImageNet error rate improving. And finally to the point where we've kind of saturated the data set. OK. So one potential problem with this is that although we've made progress on well-defined data sets and metrics, this doesn't necessarily lead to learning methods that are very robust and well-justified. OK, so my work is kind of on developing mathematical foundations of when and how deep learning works. So today I'll talk mostly about stochastic gradient descent applied to deep architectures, when it can find global minima of the training loss, and also when stochastic gradient can generalize on unseen test data. OK, so the fundamental question of machine learning is when you can achieve good test error or high test accuracy. Roughly speaking, we always think of the test error as decomposed to your optimization error. So this is whether or not how well the optimizer atom or SGD works. And the second is the gap between generalization error on test and train. So the first question will be, does SGD actually find solutions of low optimization error? And second is, when do these solutions generalize well? So the primary difficulty is that the loss landscape is non-convex. Essentially, whenever you use anything beyond a linear model, the loss will be non-convex. And then gradient descent will get trapped in saddle points and local minima instead of finding the global minima. And we know in the worst case this is unavoidable, that if you can solve non-convex optimization, this would be P equals NP. OK. So the best you can hope for is that gradient descent finds a local minima. In fact, surprisingly, this was not known until 2016. So with some collaborators, we proved that gradient descent with random initialization will converge to a local minimizer and not a saddle point, which is a very intuitive result. So it's surprising it wasn't known. And in fact, we established this for essentially all commonly used algorithms, coordinate descent, mirror descent, ADMM, these all converge to local minimizers, thus establishing that saddle points are really not an issue, at least in the sense that you'll never converge to one. However, the goal is not to just find a saddle point and a local minimizer, and typically we want to find a global minimizer. And sort of what we notice in practice, at least noted for the past 20 years ago, is that it's easier for SGD to optimize bigger networks. This is somewhat intuitive. If you use a bigger network, you have more parameters, and thus you can fit more data points. OK, so starting around 2017 and all the way to 2019, I worked with collaborators to kind of make this intuition formal. Our first result for shallow networks in 2017 showed that if the width of the network is bigger than the number of data points divided by the dimension, then gradient descent converges to a global optimum with 0 training error. And in 2019, for deep networks, we showed if the width is larger than a polynomial of the number of data points, then gradient descent converges to a global minima also of 0 training error. So these two theorems combined show that SGD and gradient descent will find solutions of nearly 0 training error. Of course, 0 training error is not the final goal. We would like to talk about test error. So more recently, with my postdocs, I worked on the problem of understanding how self-supervised learning works and why self-supervised learning can learn solutions of low test error. So sort of the most canonical method I'll look at is context encoders or mass autoencoders, and also including mask language modeling, such as BERT. So the idea is that in self-supervised learning, you first solve some auxiliary or pretext tasks, such as filling in blanks. And then you fill in these blanks, you throw away everything, the last layer of the network, or the last few layers of the network, and retrain on labeled data. Thus, you keep this function psi that's learned from unlabeled data, and you train a new linear probe. And the question is, why does this new linear probe on the representation function psi still work well? It was trained on data that saw no labels. This is also the same case in language modeling. You train on completely unsupervised data, and you can do well on many, many different downstream tasks, which is somewhat mysterious. OK, so we kind of established 2 years ago that for under pretty weak conditions on how the pretext tasks are chosen, then the error rate now is the number of parameters in the linear probe divided by the number of labels samples. So typically, the number of parameters in the linear probe is very small, order of hundreds. In contrast, if you do not use self-supervised learning, the error rate you should expect is sort of the number of parameters in your ResNet divided by the label sample size. So these would differ by an order of several hundred or several thousand. So you would go from typically a linear probe has hundreds of parameters, a ResNet has, say, 50 million parameters or something. So kind of the goal here is to establish how unsupervised learning can still work. And that's all I have to say. Thank you.
Thank you. All right, so I would like to introduce the next person, a young man of the University of Southern California. I would like to invite him onto the stage for his presentation. Yes. Here we go. Please welcome him with a big round of applause.
Right. Hi, everyone. I'm Hyun. I'm an associate professor of the computer science department at USC. I'm also the Viterbi Early Career Chair. I also founded Quest Labs, a company working on redefining the human-AI collaboration. I'm being the CEO of that. It's my really great pleasure for receiving this prestigious award, and I want to share a little bit with you about the sort of rethinking process I had once seen the great potential of ChatGPT and GPT-4, and obviously the dev days from OpenAI just early this morning just help us to rethink about what is the next stage for the collaboration between human and AI. Obviously, in the past 5 to 10 years, one thing that the whole NLP, the natural language processing community, be trying to do is to build very small customized model that can surpass average human performance on a certain problem, right? For example, reading comprehension of articles, summarizing text, translation things, and so on, right? And that we got pretty good success in early 2020, where transformer architecture came out and data-driven approach by huge compute make it successful. Things like BERT came out, and we suddenly have superhuman performance on many of the tasks. And then in the past 2 years, the next big question natural language processing community asked is, can we turn this smaller, specialized model into one gigantic generalist model, right? That can work on a wide range of different tasks and problems. And we think, as a researcher, we think we are very far away from that. We were thinking about maybe 20 years, we're gonna achieve that from 2020. And just suddenly, when OpenAI dropped ChatGPT, and in a few months, GPT-4, these things actually start happening, and pretty surprising to us. However, we found out a lot of interesting problems, or we can call it issues or shortcomings from these large models, and still make us very puzzled about how these models work and what are the ways to make them more aligned with humans in terms of the trustworthiness, in terms of reliability, and in terms of robustness, right? One interesting thing we recently see is called reversal curves. Basically, when you ask questions about some popular entities or persons or animals, the GPT models can do very good job in giving you a lot of details about those persons, right? In this example, if you ask about Tom Cruise smarter, there's no problem. Different generations of these GPT models can do well on those questions. But the interesting thing these researchers try is to ask the questions in a reverse order. They actually ask, who is Mary Pfeiffer's son, right? Basically the same piece of fact, but they just ask in a different direction. And then we'll start seeing very interesting failure modes from this large model. So that's that. If you present this challenge to any of the average human who can answer the first part of the question, they usually can answer the second part of the question. They have a very high performance, close to 99%. But we're not seeing models can do robustly on that front. So that's very puzzling, right? So really, the next thing here is, what is the ultimate alignment problems between human and AI, and how to achieve that on problems where we already see models are far better than average human, right? And my observations in the past year and so is that on many fronts, these large models, they can already surpass average human on some of the tasks. So we're talking about answering information-seeking questions. Because of this model, they have a very large memory that can basically store very compact representations of the entire Wikipedia and the entire GitHub and the entire web forums like Stack Overflow, right? So they really are very powerful in terms of retrieving knowledge and answer questions in a sort of a precise way, even though we see lots of hallucination issues, but the progress has been tremendous. Right? They can do very good job on summarizations and editing of text. And even we think it's very good sort of a starting point for you to build up business proposals or even recommendation letters. Even though the content might not be really reliable, but they give you very good structures to start with. But in contrast, we see they are still falling behind humans on some of these really crucial capabilities, right? Like the robust reasoning that we just saw from the reversal curves. And then they don't really have a clear mental model or the model of the world surrounding them. So then they are not doing really good job in terms of pragmatic reasoning. And also, we know they are still far from understanding different cultures or regions' social norms and moral values. And this sort of restrict the application of this model to many of the really potential places, right? Even though they can be a very good machine to answer questions and then do repeating jobs in a very human-like way, we still are scared about deploying them to more like high-stake applications because of what these humans are still good at. So I'm going to share with you a little bit about 2 topics that we've been working on in the past year and so. Number one is we've seen great potential for these large models to do self-rationalization, or in other words, you can ask them to explain step by step what's their reasoning process to reach to a certain answer for a given question, right? Chain of thought prompting become empirically pretty successful and attractive, even though we're seeing a lot of downside of it. But one place is we envision this can really help bootstrap the entire human society is applying this step-by-step reasoning process to facilitate model explanations about scientific knowledge and really to use them to serve as a facilitation of educations to transfer the knowledge from one population to another population to bridge the knowledge gap. Obviously, the problem many of you probably heard about is the hallucination issue, right? And the fundamental thing behind that is there's so many ways you can explain one thing to another person. And these different explanations, they can serve different functional purpose, right? For example, if you ask someone, if someone say, I love buffalo wings, and ask, do they enjoy capsaicin, right? And the other person say yes, and then you follow up with a question, why? There's many ways you can actually do the follow-up conversation. You can just simply say, because everyone love buffalo wings. This is a kind of a relatively dull explanation, but it can still make the conversation continuous. It doesn't look like a totally unhuman-like responses. But really, maybe when you ask this why question, you are trying to understand some scientific knowledge behind that, where an explanation like the bottom one, buffalo wings are fried chicken wings covered in a spicy sauce, spicy food are provided, they are spiced from capsaicin, from peppers. This will have a higher utility in terms of the knowledge transfer purpose, right? I'm not saying all this like some explanation doesn't make sense, some explanation makes more sense. I think from the pragmatic perspective, if you're doing knowledge transfer and then education, there will be some explanations that are far more plausible than the others, right? So one effort we've been making in the past few months is to try to build up this human feedback loop to provide reward-based updating to this language model so we can have a more controllability in terms of how the model explains things, right? For example, if your ultimate goal is to build an education assistant to try to give more mechanistic explanation rather than teleological explanations to the audience, for example, they are children in school, then you definitely want the explanation can help people to generalize to unseen situations, to unfamiliar cases, right? So to that end, here's the framework we propose, right? So we first ask your existing systems on the left-hand side, showing the icon to generate explanations for a given question and the answer it gives. And then we take this explanation, we send them to 2 simulators. And this simulator, one of them is taking the explanations to answer a new question that is topically relevant, right? In this case, if the original question is about, would ramen be bad for someone with heart failure? And one interesting generalization questions you can use to test the rationale is, should people with heart failure intake too much sodium? It's topically relevant. They are sharing some underlying reasoning process and requiring the similar facts. So we take the rationale, we run through a simulator, try to answer that new question, and then we compare the performance with a simulator that doesn't use that rationale, and also try to answer the same question, and we see what's the performance improvements from the simulator using the rationale, right? And that formed the reward, what we call GenU. This reward is a proxy for the utility of the rationale. And then we can take that reward, go back to update the language model. Ultimately, we want the language model to generate rationales that can have a larger information gap between a simulator using rationale or without using rationale. And this turns out to give us some good controllability to turn this language model to be more factual, to be more faithful, and have a higher utility when giving explanation, and therefore building a better sort of a system for education purpose. I talk about how AI could actually do knowledge transfer to help with education. There's another direction of this whole cycle, which is eventually how humans of different subpopulations and culture background gonna improve AI in this very special moment, right? We are in a sort of inflection point that AI is already a much higher performer than average human on many problems, right? But we still see a lot of like culture gaps. So what we envision here is that rather than directly building data sets of all these different purposes and tasks, we want different subpopulations. We're talking about maybe the employees within a corporation or the students within the same major. They could do their own sort of customized language model on the edge, right? And these smaller pieces of language models, maybe there's only 10 billion parameters on each of them, there could be a very good privacy-preserving way of merging these smaller language models and turn that knowledge into a larger or gigantic consolidated language model. And this process happens continuously, not just one time. Obviously, there's many technical challenges. We've been working on that, and two things I want to highlight. Number one is how we do model merging in a privacy-preserving way. And obviously, this is more important on places or application domains where people are really conscious about sharing PII information, right? So a traditional methodology of putting all the data sets together and then do a multitask training is no longer a good option because of the privacy concern. Rather, in the iClear paper this year, we found out that with just the embedding matrix from each of these smaller models, we can actually have a very nice closed-form solutions to merge these different models into one bigger models that have the shared knowledge all consolidated together. And the nice thing about this approach is, number one, it's computationally very efficient because it's a whole closed-form solution. And then there's privacy preserving. You don't need to pass your training data from each of the subpopulation to the centralized server. And then number three is it can work with a large number of arbitrary numbers of models to do the merging rather than have to do this like one by one sequentially. And before I finish, the next one more things I want to highlight is the continuous learning perspective that I show in the diagram. Right? We are very sort of excited about the capabilities of the model, but many cases when we customize them to certain tasks, they forget about the general knowledge they have. That's what we call catastrophic forgetting issue. And the whole community has been working on this for years, but really to make this practically useful, there's still a lot to be done. So one trial we did earlier this year was having this distillation loss function that can take your previous model checkpoint and then the new model that you are updating and then compare their prediction logics and form a KL divergence loss between these two sets of logics to push the model to not to go too far away from its previous checkpoint. And that process we call replay memory-based distillation has been proven to be very successful in both the pre-training process of the language model. For example, updating your language model from last month's data to this month's data. And also they are very good in terms of helping the model memorize the general knowledge when you fine-tune them towards a certain domain. For example, literature about semiconductor research, right? So really, we think there's very interesting problem to be continued to study on this continued learning space. So that concludes my talk with my sharing of our research. Again, really appreciate the opportunity for sharing our work here and appreciate the work. Thank you.
Thank you, really. Thank you very much. I really enjoy your presentation. Now you may return to your seats. Thank you, and congratulations, young man. All right, and the next speech is going to be by Emma Pearson from Cornell University. As Professor Pearson is abroad, we'll meet her via a video call. Professor Pearson?
Thank you very much for the opportunity to speak to you today. It's a tremendous honor, and thank you as well for this award. Today, I want to talk to you about using machine learning and AI approaches to reduce inequality. To frame this talk, though, I want to start by pointing out that we've seen many examples of the ways that algorithms can be biased and can increase inequality. For example, we've seen examples of language algorithms which work better in English than in other languages, or computer vision algorithms which work better on people with lighter skin than people on darker skin, and many other examples such that literally multiple books have been written on exactly this topic. And if you're interested in learning more about this topic, actually, we're about to release a Coursera class on it, which we hope will be available to people all over the world. And as part of that class, we're sort of talking about 10 basic principles for designing algorithms that are fair and that do not increase inequality. And one of the reasons I think I've thought so much about those 10 lessons is that in one way or another, a lot of my work for the past 5 or 10 years, a lot of the papers I've written have been about those lessons in one way or another, and how to build algorithms that do not increase inequality. But today I want to talk to you about some of our work in a more optimistic direction, about how AI and machine learning, properly applied, can also help us understand and reduce inequality. And to make this point to you, I'm just going to tell you 3 very quick stories about understanding inequality in pain, policing, and mobility. So, in our pain project, which was published a couple years back in Nature Medicine, we study knee osteoarthritis, which is a very common cause of pain in older folks. A lot of people in this room are going to develop it if they haven't already. And there's a lot of racial and socioeconomic inequality in knee osteoarthritis pain. For example, poorer patients experience greater pain. The interesting mystery is that this pain gap persists even when we control for how severe the doctor thinks the osteoarthritis is, as measured by looking at an X-ray of the patient's knee. So why is this? One possible explanation is that there's something outside the knee entirely, like higher life stress, which causes poorer patients to experience greater pain, even when their knee disease is no more severe. And that's why controlling for the doctor's assessment of the knee X-ray doesn't do that much to narrow that gap in pain, because it's something outside the knee entirely. It can't be seen in the image at all. But there's a second possibility, right? And that's that the doctor is missing something. There is something additional to be seen in that knee X-ray, which could help us narrow the pain gap and better understand inequality in pain. And so what we do is we use a deep learning approach to try to distinguish between these 2 possibilities, to search for the signal that the doctor might be missing. In particular, we train a deep learning algorithm, a convolutional neural network, to predict pain from knee X-rays, looking for additional signal in the knee, which might help explain the pain gap. And we find that our deep learning algorithm does find additional signal within the knee for predicting pain, and that when you control for this signal, you can narrow that pain gap and reduce inequality in pain. This suggests that the measures that we traditionally use in health clinics might fail to capture all the physical knee features that explain some groups' greater pain levels. And it also suggests that algorithms can find signal and medical images that human doctors miss, potentially helping us understand and reduce inequality. Let me tell you the second story about understanding inequality and discrimination in policing. So, I work in the United States, where there's been a ton of concern about racial discrimination in policing, where the police treat drivers of certain races, Black and Hispanic drivers, worse than they treat white drivers. So what we did in this project was we worked with journalists to pull together data on hundreds of millions of traffic stops throughout the United States. And then what we did was we took that data and we applied AI methods to basically try to detect and quantify racial discrimination in police behavior, to try to see whether the police were treating some drivers worse. And we in fact found evidence of racial discrimination against Black and Hispanic drivers in both when the police stopped the driver in the first place and when they decided whether to search them after the stop. And we released this analysis, and it has in fact sort of shaped how policing is conducted in major American cities like Los Angeles. The third story I want to talk to you about is about understanding inequality and mobility. And when I say mobility, what I mean is cell phone mobility data, tracking where people go, basically the patterns of human movements. Because of course your cell phone tracks locations over time, and if you aggregate data from millions of cell phones, you can get quite a rich picture of human mobility. So we've taken this very rich data and we've used it to study various aspects of inequality. The first thing we used it to study was COVID-19, because intuitively, right, the spread of COVID-19 depended very much on the patterns of human movement, how people were mixing with each other. If you had a lot of people in a restaurant, that was a dangerous situation, right? And so what we do basically is we apply machine learning and AI approaches to this raw mobility data to try to infer networks of human interaction. And then we put a probabilistic model on top of those networks of human interaction to model the spread of COVID across that mobility network. And we use that to understand why there was inequality in COVID infection rates. For example, we saw in the United States that poorer neighborhoods were getting infected at higher rates. And we were able to sort of link that back to ways in which their mobility patterns were different. And this project, too, we were able to use to help inform healthcare decision-making. For example, how, which restaurants or how many restaurants it would be safe to open and how densely they could reopen in a way which was hopefully more equitable and more fair to the population as a whole. In subsequent work with mobility data, we've used mobility data to measure something called segregation, which is to say how much the rich and the poor mix in their daily lives. And we care about segregation because segregation can be quite a bad thing. Among other things, it reduces economic mobility, so sort of your ability to improve your economic circumstances in life, and can increase inequality. And it has a bunch of other consequences as well. But it's hard to measure, right? Because it's hard to know, like, how, who everyone is mixing with at every moment of the day. And so what we do is we use cell phone data to measure this as well, because if you can sort of track where everyone goes, you can track when the rich and the poor come into contact with each other. So we develop scalable and efficient algorithms which are able to, basically be applied to the minute-by-minute locations of 10 million people. And with this data, we find a way to infer how rich or poor someone is from where they move around. We also are able to infer which pairs of people cross paths, and then we develop a statistical model on top of that path-crossing network to come up with new measures of human segregation. And in fact, we show that segregation is higher in larger cities, which was not known from prior work. All right, so those are the stories I wanted to tell you about today. It is undoubtedly true that machine learning and AI methods can, if you don't apply them properly, increase inequality. And this continues to be a major focus of my research. But I want you also to remember that properly applied, they can help us better understand and potentially reduce inequality. And I've told you 3 stories about that today. Thanks very much for the opportunity to speak, and again, for recognizing me and my collaborators with this award.
Thank you. Thank you for the great presentation. Congratulations. All right, so we have 2 more awardees are now here with us online. The following speeches, Virginia Smith from Carnegie Mellon University. Professor Virginia Smith is now here with us online.
Wonderful.
Yes, fantastic. Good to see you. Congratulations. If you are ready, please begin.
Thank you. Yeah, thank you so much. I'm incredibly honored to receive this award and very excited to speak with you all briefly about some of my research in developing foundational tools for the field of federated learning. So to provide some motivation for what I mean by federated learning, we can start by thinking about some exciting recent applications of machine learning and AI. Maybe applications like chatbots or related applications in language modeling or voice recognition, applications of machine learning in healthcare, or smart homes or smart cities. Crucially, all of these applications of machine learning rely on data. And where is all of this data coming from? It's often not coming from just a single person or a single device, a single mobile phone user, a single patient in a single hospital, or a single sensor in one of these networks. It's coming from multiple people, multiple devices, often from multiple organizations and from entire networks of sensors. And the key idea in federated learning, very simply, is to be smart about the fact that this data is being born at the edge and to think about moving the machine learning pipeline to the edge as well. So rather than taking all of the data that's being generated across these disparate silos of data and moving it to some central location, the idea in federated learning is to try to move as much of this machine learning pipeline to the edge as possible. And why would we do this? What are the advantages of federated learning? One is that it can help to reduce storage costs. It can reduce strain on the network. It can reduce the amount of messages that are being sent and the amount of data being sent over the network. It can allow you to more quickly incorporate new data that you're seeing at the edge. And then a major benefit of something like federated learning is that it can help to potentially improve privacy and security of sharing your data. Okay, so for this reason, over the last several years, there's been a tremendous number of applications of federated learning that have been deployed. For example, from groups like Google and Apple and Meta, who have deployed federated learning solutions over networks of mobile phones, for example, to power models for next word prediction in mobile keyboards. But there's also been applications of what is known as cross-silo federated learning as well. So learning over smaller networks of siloed data, like across multiple hospitals or financial institutions. For example, powering more expressive models for tumor detection without sharing raw patient data between hospitals. So crucially, all of these applications of federated learning really boil down to solving some distributed learning problem. You need to fit some model to your data, and that data is distributed across a network. There's been a lot of work in thinking about how to perform learning in distributed settings. In particular, there's been a lot of work on this in data center settings. So thinking about how to distribute the learning process across multiple servers in a data center. But there are a number of challenges that make this setting particularly unique and potentially difficult. One is that in federated settings, whereas communication is always a known bottleneck in distributed computing, here you might be learning over networks of thousands to millions of devices. So the networks can be very slow, they can be very large, and they can also be very unreliable. You might have practical issues like someone turning off their phone or their device, and this can really affect how you can think about using this network as a computing substrate. There are also terrific concerns around privacy and security. This is a major motivation to do federated learning in the first place, but you're still sending messages across the network, and there are still various ways that sensitive information can be leaked. So it's really important to think about how you can still maintain privacy and security throughout this distributed learning process. And finally, a major way that federated learning differs from something like distributed data center computing is that because the data is being generated at the edge, and we're keeping the data at the edge, there can be tremendous amounts of heterogeneity, both in terms of the data that's being generated and the underlying devices that are used for training. So for example, in the example we talked about of learning over mobile keyboards, it could be that people speak differently. They generate text in slightly different ways. And this can affect how the data looks from one device or one client to another. Okay, so over the last several years, I've had the great fortune to work with a terrific group of students and collaborators to develop foundational tools for this area. This has involved developing techniques for efficient distributed learning, so focusing on making this scalable to possibly networks of millions of devices. Also dealing specifically with this issue of heterogeneity. So how can we properly train over heterogeneous data and systems, and how should we think about modeling heterogeneous data? And finally, a key component of this as well has been thinking about these issues of trustworthiness, developing tools for private federated learning for improving issues such as robustness and fairness in federated settings as well. And these tools have been used to deploy applications along with partners at places like Google and Meta, powering things like smart home anomaly detection with partners at Symantec, thinking about developing tools for things such as pandemic forecasting across hospitals in a privacy-preserving way. And our tools have also been deployed in common federated learning libraries. We've developed our own libraries and benchmarks ourselves. So we've developed this LEAF benchmark, which has become a very common benchmark for the field of federated learning. And we help to run this weekly worldwide seminar on federated learning. So if you're interested in this space, I would definitely recommend checking out this seminar that is open to the public that we put on once a week. I don't have time to talk about all of these areas in detail, but I wanted to mention today just one area that we have worked on a lot over the last several years that we found has been particularly important for addressing many of these challenges, for improving the efficiency and accuracy and trustworthiness of learning in federated settings. And this key idea really boils down to this issue of heterogeneity and thinking about how to best model data that might be coming from diverse sets of clients over a federated network. So on one extreme, you can imagine if you have different devices in a network generating data, you could learn completely separate sort of local models, one for each device. This is very personalized to the unique heterogeneous behavior on each of the devices, but it's sort of missing the point of federated learning, right? Ideally, you can learn from peers in the network and you can learn more expressive models by sharing information between these devices, right? For example, for the application of mobile keyboards, there's probably not enough rich text data on a single person's mobile phone to learn a powerful language model. On the flip side, the sort of current practice is to think about maybe just learning a single model from all of this data. So while this allows you to share information from peers in the network, it also lacks some of this personalized behavior. So ideally, we might want something sort of in between these two extremes, where we can both appropriately model the heterogeneous data that's being generated in these networks, but also learn from peers in the network. And this is something that we found to be particularly effective through a technique known as multitask learning. At a high level, the idea is that we can learn separate models, one for each device in the network, but then we can also learn about the relationships that exist between these models or devices or tasks. So for example, we might learn that all of the devices in the network are related, and we're learning sort of the weights on the edges in this graph, that there are outliers that exist, maybe that clusters or groups form in the network, or maybe that there's some asymmetric relationship. So we can learn these relationships directly from the data in a federated setting. And doing so has many advantages. So appropriately modeling this heterogeneous data can improve the accuracy of learning in federated settings. It can also improve robustness to corrupted data or adversarial attacks in federated settings. It can improve the fairness of learning in federated settings. So it can help to boost the performance across clients that might look different from other clients. And it also has tremendous benefits in terms of privacy as well. So multitask learning in particular can retain the sort of accuracy benefits that you see in non-private settings, even when you deploy it in private settings. And it can also have additional benefits relative to just learning a global model, even when you don't necessarily see those benefits in non-private settings. So for this reason, this idea of personalized federated learning and multitask learning, we've seen that it can be and have shown and proven that it can be useful for many different aspects of federated learning. And we've also deployed it in practice in several scenarios. So this is a key technique that we used to develop smart home anomaly detectors in partnership with collaborators at Symantec. Ideas around personalized federated learning are being used in many different aspects of learning across mobile phones, including for next word prediction on Google's keyboard. And this was a key technique in recently winning a prize challenge around privacy-preserving pandemic forecasting across hospitals. Okay. So I will just say very briefly a little bit about where I think the field is going and what's exciting in this area moving forward. One thing I wanted to point out is that this is an area that I think is being particularly affected by something like these large pre-trained foundation models. And it's being affected in two ways. One is that we're seeing more of a need to support these models. So improving the efficiency of fine-tuning inference and evaluation and developing new models and understandings of privacy when using these pre-trained models in federated settings. But also I want to point out that federated learning at its heart is dealing with a lot of key issues that are useful for thinking about both developing and updating these pre-trained models. So thinking about training in a very, very efficient and decentralized manner, collaboratively combining updates and doing so in a way that enables trustworthy performance. Okay, so moving forward, I'm excited to see the field continuing to grow and taking on sort of bigger and larger, broader perspectives, especially around the idea of collaborative learning more generally. So maybe not training a model from scratch in a network of mobile phones, but also thinking about broader perspectives on collaborative learning, updating models after they've been trained, learning across multiple sources, across multiple stakeholders. And I think there's going to be a lot of interesting challenges here. Some of the challenges we've talked about so far in federated settings, like learning from multiple heterogeneous sources, but also potentially new challenges, like thinking about how to incentivize clients to participate and share their data. So thanks, that's all I had.
Thank you. I really enjoy your presentation. Thank you very much and congratulations. Last but not least, we're going to hear from Connor Colley of the Massachusetts Institute of Technology. As Professor Cornell is also abroad now, he is now online.
Terrific. First of all, I'd like to thank you for the opportunity to be here and share some of my work with you today. Again, I apologize that I can't be there in person, but it's really a pleasure to still be able to join you remotely. My research focuses on the intersection between AI and chemistry. And so I think a lot about small organic molecules and the way that we can use them to achieve useful purposes in solving challenges in human health, in sustainability, and in many other applications. And so small molecules are a very remarkable modality in that just by rearranging the atoms in a molecule and using the same building blocks of elements, we can achieve a very diverse range of function. And so the properties that make certain molecules good as therapeutics would be very different than the properties that make molecules good as pesticides, but the processes by which we discover them share many commonalities. Now, one of the challenges is that chemical space is truly vast. And this is both a blessing and a curse because the vastness of chemical space is what gives small molecules the ability to achieve this diverse range of functions. But at the same time, it makes it a very challenging search problem. And so that's why, to search this vast chemical space, we've turned to the use of different computational tools, including the use of artificial intelligence. So the discovery of molecules is almost always an iterative process by which we will design structures, we'll go into the lab and test them, we'll measure their properties, and we'll use that information to help us design an even better set of molecules in the next round. And so the research of my group has tried to look at, broadly speaking, the different ways that we can accelerate this process and use models to help us augment human intuition and expertise. So we and others in the fields develop models that help us understand the relationship between molecular structure and function. We build models that help us design new molecular structures and come up with ideas for molecules. We also think about chemical synthesis, which we'll touch on briefly in this overview. And we've started to think more about analytical chemistry and the use of models to help us understand what we've made inside a reaction flask. And we'll focus on the question of design because design is a very fundamental problem. It's the question of saying, given all of the information that I have access to right now, what molecule is the most useful one to make or test next? And so to talk about design, we'll start with this idealized landscape of a structure-property relationship. So this colorful surface represents a cartoon version of what happens if you vary molecular structure. You might expect that some will have better properties than others. Again, this property might be a biological activity measurement if we're doing drug discovery, or it could be an electronic property if we're doing materials discovery. And so in this paradigm of screening, we'll take these surfaces or take these relationships and we'll query the model. We'll have trained a model through maybe supervised learning and we'll ask for all of these new chemical structures that I haven't seen before, haven't measured before, what might their properties be? And we can use this to identify the chemical structures that are predicted to have the best properties. Now, of course, with increasing interest, it'll come as no surprise that people are using generative techniques to not just screen molecules, but now propose new ones and directly find structures predicted to exist at these maxima. And so generative design for chemistry is very exciting because it's this notion that we can use AI to help us invent from scratch new molecular structures that might have unprecedented properties. And so we can teach generative models to propose new molecular structures, atom by atom or sort of fragments by fragments, using many of the same techniques that you'd use for text generation, right? We can formulate this problem of molecular design as the generation of text or characters, or the generation of a graph. This is an animation showing an example of one of our models that we've trained to propose a molecule that maximizes some predicted score relating to the efficacy of a protein molecule, which is a new modality in drug discovery. And so this molecular structure is designed to bring together two proteins into close proximity, and then one protein will be tagged by the other for degradation by the natural host's proteasome. Now, sometimes we'll design these molecular structures as graphs, as we're doing in this case, atom by atom, bond by bond. Sometimes we also design them in three-dimensional space. So here's a different animation showing the results of taking a trained model for molecular design, where we can query a target structure in this blue outline or this blue mesh, and we get this resulting pink suggestion, where the pink shows a new molecule that the model has invented that it thinks can achieve that target shape. Now, there's many different approaches to do generative design of new molecules, but one of the shared challenges between most of them is that sometimes the models are, I'd argue, too creative. They invent new structures that technically don't violate any fundamental laws of chemistry, but at the same time, they're structures that don't look very reasonable. This is a little bit related to what Professor Bengio was mentioning in the opening keynote about misalignments. It's a different sort of misalignments, but it's the fact that when we ask these models to optimize molecular structures for one certain property, if we don't include synthesizability or stability as one of those properties, it might find structures that actually don't achieve the real objective we have in mind, because these are not the kinds of structures we'd want to give to a chemist to test in the lab. And so this has motivated us to think about chemical synthesis and the different ways that we can use AI for this task as well. And yes, we can train models to take molecular structures that we'd like to synthesize, and we can query these models with a new molecular structure it hasn't seen before and get this large recommendation of options. And depending on the molecule that we're asking it to help us make, sometimes we get one suggestion, sometimes we get 1,000 suggestions, sometimes we get 0 suggestions of different recipes that tell us how can we possibly achieve this target molecular structure through chemical synthesis of commercially available building blocks and different reaction transformation steps. Now, there's many different approaches to do this task of synthesis planning, but something that we have been thinking about recently is, why do we need to treat these as two decoupled steps? And so traditionally, we do think about molecular design as this distinct task from chemical synthesis. But instead of doing that, let's try to combine them. And so we and others have started to reformulate this task of molecular design so that instead of asking our models to propose molecular structures as a task that requires them to think atom by atom or fragment by fragment, we ask our models to propose experimental procedures that give us the recipe or encodes the production of a new molecule. And so in this way, we're asking our models to think in the same terms as a human chemist. Right? What building blocks might you buy from your chemical vendor? What types of reactions might you run in the lab? And so we ask our models to basically act as a virtual chemist and put together these building blocks through chemical transformations we know how to run. And so what they come up with is then associated with this experimental procedure and not just a molecular structure. So what this looks like, or what this can look like, is that our model sees a blank canvas and it knows that it needs to start somewhere. And so it knows that it needs to begin by selecting some commercially available starting material, some physical chemical that it knows it can purchase. After it does that, it might decide to run a particular type of chemical reaction. It recognizes here that it needs a reaction partner. And so it also predicts and selects a reaction partner from this large set of commercially available starting materials. And it repeats this process over and over again, sort of choosing new reactions, choosing reaction partners, until ultimately it decides that it's finished. And once it's finished, we end up with this molecular structure as its proposal, and we can apply the same sorts of scoring mechanisms that we might otherwise. If we're doing drug discovery and we have a particular protein target in mind, we might use techniques to estimate the binding affinity to that protein of interest. We might estimate other sorts of properties for other applications. But what's really important to point out is that not only does this kind of model give us the structure that it's recommending our chemists test, but it gives us the recipe. right? By generating this structure, it's also generated the recipe by which we can make this new molecule. And so, because we do have this really complicated search problem when we think about using AI for the discovery of new molecules and new materials, it makes sense to turn to AI computational assistants for help. But unless we align generative AI with the realities of the experimental or physical world, we can't ensure that it's going to recommend suggestions that we can actually make in the laboratory. And so we need to make sure that the models are thinking in the same terms as we are, as human experts in these fields. And so there's, of course, many challenges, even if you've addressed the design and synthesis challenges. We need much more effort, I think, in improving the evaluation of molecules, not just the design of molecules. And there's also, of course, plenty of opportunities for more actual experimental demonstrations of this concept and showing how this can impact drug discovery, sustainability, and other applications where these small organic molecules can have a real impact on the world. And so that's what I'd like to share with you today, and I'll of course acknowledge the fact that none of this work is possible without a terrific team of researchers and students and other collaborators and funding agencies. And again, thank you so much for this recognition. My apologies that I haven't been able to be there in person to celebrate, but thank you for this opportunity, and thank you for your time.
Thank you very much, Professor, for the great presentation. So also congratulations on the results of the competition. Thank you once again. So now, ladies and gentlemen, all of the scheduled plenary session have now concluded.